Hello, this is Philip Myers of PEMY Consulting. Welcome to Engineering Units for the Plant Engineer. This is Unit 5. We have 3 examples for you. In the first example, we want to find the pressure at the bottom of a tank. It has a specific gravity of 0.7, a liquid height of 48 feet. G is the ratio of mass densities to that of water for a given liquid. This is usually at 60 degrees Fahrenheit, but the temperature dependence is not very large, so most of the time you can forget about the need to adjust for temperature. In any case, the rho of the liquid is G times rho of water. Rho of water, of course, is 62.4 pounds mass per cubic foot. So pressure is G times rho GH, 0.7 times 62.4 pounds mass per cubic foot times 32.2 feet per second squared for the gravitational constant and the liquid depth of 48 feet. Multiplying out, we have 67,511 pounds mass per foot second squared, but pressure is in pounds force per foot squared. So we need to use our conversion factor on this computed result. The pounds mass will cancel, the seconds will cancel, and we're left with pounds force, which comes up here, per foot. So 2096 pounds force per square foot. Now we want the answer in PSI, so we have to take 12 inches per foot, square that, and divide it into the 2096. So we end up with 14.56 pounds force per square inch, otherwise known as PSI. Note that the pressure in the bottom of a tank is really not very high. It's only about 15 PSI. In the next example, we want to show how to derive the 1-foot formula. This is a well-known formula for tanks, and it appears in both API 650 as well as API 653. The formula is 2.6 G times H in feet minus 1, that's the height of the liquid, times D, the diameter in feet, divided by S in PSI, which is something you have to be careful about because of the mixed units. The standard hoop stress formula is stress is equal to PD over 2T. This, of course, is in consistent units. If we swap the stress with thickness, we end up with the required thickness for a shell course to be equal to PD over 2S. But note that the API formula, thickness design, is equal to 2.6 D H minus 1 G over S sub D plus corrosion allowance. How do we get this? Well, we can first cancel this out because that's just a fat factor for extra steel that you want to add when you order the tank. If we go back to the basic hoop stress formula, we see that P is rho GH times D over 2S. This is in turn equal to G times gamma H. So this is gamma is pounds force per cubic foot. So we have G times 62.4 pounds force per cubic foot times H in feet times D in feet. These will cancel and you're left with feet, but we want to get that into inches because in the bottom here we have inches. So we have to divide by 12 inches per foot. And when you cancel out the units, you end up with 2.6 GHD over S, and the units have canceled out to result in inches, which is correct because we're trying to get thickness. This is equal to T. Now how do we get the H minus 1? That is part of the rule of thumb worked out long ago, and it's based on this. The tank shell expands due to the hoop stress that develops in the shell, but at the bottom it's restrained by the joint here. So a good guess was that the maximum expansion of the tank shell occurs 1 foot above the bottom, as shown. And even though this is not really that accurate, it is pretty accurate in many cases for different size tanks. So that's where the 1 foot comes from. It's just a deduct of 1 foot to account for the fact that you do not get a full expansion at the bottom. So actually the hoop stresses would be very close to 0, very near the bottom. In our final example, we'll consider flow coming out of a hole in a tank as shown in the picture on the right. We'll use Bernoulli's equation, and Bernoulli's equation says that at any two points, the total of the pressure energy plus the velocity energy plus the potential energy is equal. Now, of course, it does neglect friction, but it's fairly accurate for typical fluid flow. We've rewritten that for our points A and B. We're going to take A to be here at the surface and B to be here at the point where the water's coming out of the tank. Now PA, we can say that PA is 0 psig. It's 0 pressure, 0 psig gauge, and also it is 0 here. So we can drop out this term and this term. We can also say that the velocity at point A, the liquid level, is going to be very small compared to the velocity coming out here. So we can approximate VA as also 0. So we're left with ZA minus ZB is equal to VB squared. Basically, ZA minus ZB is equal to the height. So we've written the equation in this form. Height is equal to VB squared over 2G. And you can see VB is right here. Solving for BG, we get Torricelli's law. VB is equal to the square root of 2GH. So velocity has been converted from potential energy, the height of the liquid, into velocity. Now we want the flow rate, we don't want the velocity, so we need to take the velocity times the area. Now there are two correction factors, C sub C and C sub V. C sub C is called the coefficient of discharge, or discharge coefficient. It is a correction for the fact that when you have liquid spraying out of a hole, there's a vena contracta where the area of this reduced area is about 0.6 times the area of the orifice, where the orifice is right here and flow is going through it. C sub V is a velocity correction factor. It's pretty close to 1. It's about 0.95. So you can forget about these details and just remember that C, the correction factor, is about 0.6 times the area of the orifice times the square root of 2GH. And of course, whether the orifice is worn out or sharp is important. This assumes a sharp-edged orifice. So let's look at the units. Q, we want in meters cubed per second. We have C, which is dimensionless. A is going to be in meters squared because it's an area. We have the square root of 2 times the gravitational constant, that's meters per second squared, times H, which is in meters. So multiplying this out, you get meters squared times the square root of meters squared per second squared, and you end up with meters cubed per second. This is flow Q, and that is exactly what we want, a flow rate. So this is a simple way to compute roughly the flow through a hole under pressure. Thank you.